I've been thinking a lot about the next language, the language that will replace JavaScript. I believe that there has to be a language after JavaScript, because if it turns out that JavaScript is the last language, that would be really sad. But it can't stop there. Think about your children, right? Your children deserve a better language, don't they? Of course they do. So the current plan is we'll just keep adding more and more things to JavaScript, but ultimately that doesn't get us to the next language because there's too much stuff in it. That's part of the problem. So I want to talk about the post-JavaScript apocalypse. But there's some people who think that the title of this talk is wrong, that it should be the put JavaScript apocalypse. All right, so not the post-JavaScript apocalypse, but the put JavaScript apocalypse. And there are other experts who say, no, that's not the right title. The right title is the patch JavaScript apocalypse. This confusion, post, put, and patch, is due to REST and due to HTTP. HTTP contains 3 commands for sending something to be stored on a server. And the 3 commands are almost identical, but not quite. And so there's a lot of confusion, a lot of argument among the experts about which one you should use in any particular situation. So having 3 commands to do one thing doesn't make HTTP and REST richer and better. It makes it worse. It makes it more confusing and produces more opportunity to make errors and to have failures, and that's bad stuff. So having too many commands in the system is an example of clutter. When systems get cluttered, they're harder to think about, harder for us to share, to work together with. It becomes a problem. And clutter, in general, is a problem in our lives, that we work hard, we make money, we buy things, we buy stuff, and we take the stuff and we put it in our homes. And eventually, we have too much stuff in our homes, and our homes are cluttered. And we think of the value of our possessions in terms of the acquisition cost, or maybe the replacement cost. But we don't think of the value in terms of what does it actually provide us. And if we have so much stuff that some of it is hidden in piles or hidden in drawers or in closets where we can't see it, we're actually getting very little value from the stuff. And in fact, if you have too much stuff, the extra stuff makes it harder to realize the value of the other stuff because you can't find it because you've got other stuff that's in the way. And sometimes your stuff is destroying your other stuff. You have it in piles and you're actually crushing the stuff at the bottom, or stuff is leaking on it. So that's a problem. So how do we get rid of clutter? Well, it turns out the world's greatest authority on management of clutter is Marie Kondo, or KonMari, a brilliant Japanese woman who goes all over the world teaching people how to remove clutter from their homes. And she's amazing. So one of the things she teaches is that you go into a room and you take everything in the room off of the shelves, out of the drawers, out of the closets, and put everything in the floor in the middle of the room. And then you pick up each item individually and you ask it, tokimeku, which means, do you throb? Do you vibrate? Do I feel something? Is this communicating to me? And if it does, then you go, oh, this must have value to me, so I need to keep it. And if it doesn't, then you don't need it. So you thank it for its service, and you send it away. You sell it on eBay, or you give it to a friend, or you donate it to charity, or you recycle it. You find some better use for it, but you don't need to keep it anymore. Now, when she's teaching in English, she doesn't say throb or vibrate, because it makes some people giggle. So instead, she says, does it spark joy? Which I think is beautiful. So you pick it up, do you spark joy? And if it sparks joy, then it means something to you and you keep it. If it doesn't, then away it goes. And so I'm thinking about clutter in programming, that we could make our programming systems much easier to use, much more productive if we could remove the clutter from them. So I'd like to apply the principle of spark joy to things in programming, but that won't work because everything sparks joy. You can look at the worst, stupidest feature of JavaScript, and there's someone who's going to say, yes, that sparks joy. And so we need better practice at deciding what is clutter and what is not, and how do we get rid of it. So I want to go through some examples about how we can think about how we can remove the clutter from our systems. I'm going to start with ASCII. ASCII is the American Standard Code for Information Interchange. It was developed in the United States for connecting teletype machines in telegraph systems. It eventually became the first 128 characters of Unicode. So ASCII is now built into the character sets of every computer in the world. And ASCII was not designed to be a computer character set, and so there are some problems due to features that it has which we don't necessarily need in computers. So for example, there are two particular characters that were both inspired by keys that were on typewriters, old mechanical typewriters. There is the tab key, the tabulate key, which when you pressed it would release the carriage and allow it to swing freely until it was blocked by a physical tab stop, and then it would stop moving at that point. The tab key was intended to make it easier to type in columns of numbers and similar sorts of things that you might want to type on a piece of paper. And the space key was modeled after the space bar, which again moves the carriage one character without printing a character on the page, so that you could have spaces between words, and that's a useful thing. When tab was specified in ASCII, they did not determine how to set a tab stop or what the default tab spacing would be. And so we still argue about that. We don't know exactly how tab should work. And so we use both of these characters in our programming, and because there are now two ways of writing programs, you can write programs with tabs, you can write programs with spaces, we argue about it. We argue about it all the time. And the argument is which way is better, and it turns out neither way is better, and everybody is expecting that the argument will end by figuring out which one is better, and that doesn't happen. So there's an amazing television show that's on HBO. Has anybody seen Silicon Valley? If you haven't, you need to buy HBO and get this show, because it's the best show ever made about programmers. It's about Richard Hendricks, who is the founder of Pied Piper. He's a programmer in California, and it's about his adventures in trying to start a software company. It might be similar to some of your adventures here. And he's a brilliant guy. He works really hard. He works so hard that he doesn't have time to find a girlfriend. You may know the type, or you might be the type. Anyway, in season 3, he meets a girl, and she's great. She is nice, she's smart, she's a programmer. She seems to be perfect for him, except she uses spaces instead of tabs. And it makes Richard crazy that he can't be with someone who doesn't use tabs, and so he destroys their relationship. So having both spaces and tabs is creating human misery on a global scale. You know, it's causing problems in our code management systems, because some people want to check in one format and the other, and it just causes confusion and badness. And there's no value in having two. So we really should get rid of one of them and end all the suffering. And so the question isn't which one is better, because if there were an answer to that, we would have figured it out by now. Both sides believe that the other is wrong when they give their reasons for why they're better. And in fact, they're both right, because all of the arguments are bogus. Nobody has good arguments in the argument about tabs versus spaces, because they're asking the wrong question. The question they should be asking is not which one is better. The question is, which one can we get rid of? Can we get rid of one? And if so, which one can we get rid of? And it's clear the one that we can get rid of is tab. We can't get rid of space because we still need the interletter space. But people who only use spaces provide proof that you don't need tabs. And so which one can we get rid of? We can get rid of tabs. So I would say, tab, you do not spark joy. Thank you for your service. Goodbye. JavaScript provides 2 characters for yeah, so I just solved the tab versus spaces debate. You're welcome. JavaScript provides 2 characters for quoting string literals. And unlike some other languages, they work exactly the same. And for a while, I tried to figure out how to make sense out of that. So I came up with rules for when you'd use single space and when you'd use double space. And eventually, I worked out a set of rules that I thought made sense. But then I saw some other people had completely different rules, and they made sense too. And it was like, so how do we decide when to use one and when to use the other? And eventually I figured out I was asking the wrong question. The question is, which one can we get rid of? And so I think the one we can get rid of is a single quote, because it's problematic because it's overloaded with apostrophe. So you can't use single quotes on strings that have apostrophes in them, so we're better off just using double quote all the time for everything. JavaScript has let and var for creating variables. And so we have 2 ways of creating variables, and some people are trying to figure out when you use one and when you use the other, what's the correct timing for each. And again, that's the wrong question. The right question is, which one should we get rid of? And I think the one we should get rid of is let. The one we should get rid of is var. We should keep let. The reason I think we should keep let is because it doesn't confuse the Java guys so much. The Java guys get really confused with var because they expect block scope to work, and var does not have block scope. So just to avoid confusing the Java guys so much, I think we should just use let. Now, it turns out we also have const, and actually, anytime I have a choice between using let and const, I will use const. Const is generally the better. It's the more pure, it's the more functional. Sometimes we just have to get dirty, and so I can't get rid of let, but when I can, I'll prefer to use const. JavaScript has 2 bottom values, null and undefined. There's a debate in language design, should a language have any bottom values at all? But nobody thinks you should have 2 of them. And JavaScript has 2. And they are not the same, although in some cases they kind of act the same, but in other cases they don't. So if you have 2 values and you expect them to act the same, and they're not guaranteed to act the same, that's a source of confusion and errors, and so I want to get rid of one of them. So the question is, which one should we get rid of? And usually if I have a choice between 2 words, I want to get rid of the longer one, just because I don't like to type so much. But in this case, I want to get rid of the shorter one. I want to get rid of null, because undefined is the one that JavaScript itself uses. If you define a variable and don't initialize it, it gets the undefined value as its initial value. If you have a parameter that is not initialized by an argument, it gets initialized with undefined. If you access a property from an object or an element from an array that doesn't exist, you get the undefined value. So you have to understand how undefined works anyway, so let's just do that. Also, type of null is completely broken, so let's just get rid of it. Now, the idea of null comes from Tony Hoare, a brilliant British programmer. He's the guy who came up with quicksort, and he came up with the idea of having null pointers in programming languages. He now calls that a billion-dollar mistake. And he came up with that figure by estimating the cost of all of the null pointer exceptions that have ever happened. And he thinks it's probably at least $1 billion by now. So we still, I think, need some kind of terminal or empty value. And In the next language, I'd like to call it null, or maybe nil. I'd prefer a shorter name than undefined. But instead of being the particular weird kind of bad pointer that it is, I think it should instead be an immutable empty object, which in a JavaScript-like language could be defined like this. I'll make a const called null. I will initialize it with an empty object that inherits nothing, which is frozen. So if you attempt to modify that object, it'll throw an exception, which is the right thing. If you attempt to call this object, it'll throw an exception, which is the right thing. If you attempt to read a property from it, you will get the null value. And so if you have a long path where you go A.B.C.E, and any of those, and you can't get to the end of that path, instead of having exceptions happening at some unexpected point, you'll just get the null value at the end, which I think is exactly the right thing. I think that would make programming quite a bit easier. So we're seeing a lot now about pure functions and pure functional programming, where pure functions are analogous to mathematical functions. In mathematics, functions are not things that do computation, they're just things that describe the mapping of one set of values to another set of values. And there's some interesting things that happen when you apply that model to programming. One is that a given input will always yield exactly the same output. So functions are not allowed to keep any state or anything which could cause their behavior to change in any way. So there's no mutation, no side effects. It's a very simple, very clean programming model. And it provides some really nice properties. First one is testability. Because a function will always produce the same output for the same input, that makes testing a whole lot easier, because once you've tested something, you're done with it. It's guaranteed it will always produce that output for that input. So testing is great. Composability is also really good, that you can take programs or functions and put them together in higher order ways and construct stuff very powerfully. And maybe the best benefit is that we have the opportunity to have parallelism. That if you have a bunch of functions that you might want to apply to an array, and those functions cause no side effects, then we could distribute all of that work over as many cores as are available, and everything works in parallel. And so with that, potentially JavaScript becomes the fastest programming language in the world. And that's a pretty nice thing. So what would it take to turn JavaScript into a pure functional programming language? It turns out we don't actually have to add anything to the language, we just have to remove the impurities. We're trying to make it a more pure language, so we have to remove the things which are not pure. For example, we have to remove the date function, because every time you call the date constructor, you get a new, different date object that has never existed before. So that is not mathematically pure, so we have to get rid of date. We have to get rid of random for the same reason. Every time you call the random function, you get a different value. That is not pure, so that has to go. The delete operator on objects are mutating objects. We can't have object mutation anymore, so that has to go. Object.assign and any of the other methods that might modify an object, we have to get rid of those. Similarly, array.splice and array.pop, push, reverse, sort, all of those that can modify an array, those have to go. Sort could have been a pure function. The correct way to have defined sort would be that you get a new array which is properly sorted, but JavaScript didn't do that. Instead, it mutates the original array, which is not pure, so we have to get rid of sort. The regular expression exec function keeps state, unfortunately, in the regular expression object, so that has to go. Assignment statements, we have to get rid of those. We can't have assignment anymore, and because we don't have assignment, we don't need vars anymore, and we don't need let, but we can still have const. In fact, const works really, really well in the pure functional model, so const is good. We get rid of for statements because a for statement requires an induction variable that's always changing. That's a mutation. We can't have mutation, so for has to go. Users, it turns out every time you interact with a user, they could do something different. It turns out humans are not mathematically pure. So they have to go. The network is not pure. You can go out to another machine, and that machine could send back something. You can't predict what it's going to send back, so those are not pure. So purity is great, and we can get a lot of benefit from purity, but we can't be totally pure. The universe is not pure. The universe is constantly mutating everywhere, constantly. And if our programs only deal with purity, then they cannot interact with the universe, and that significantly limits their usefulness. So we should have as much purity in our programs as we can, but off toward the edges, in the places where we touch reality, we have to ultimately be impure. So part of the task of programming going forward is going to be figuring out what can we do in a pure way and what has to continue to be stateful and mutating. So one of the weird features that was added in ES6 was generators. And the basic idea behind generators, I think, is really good. It's a higher order functional thing. It's not pure, but it's cleaner than global variables and things that we used to do. I don't like the way that generators were implemented in ES6. First, there's the weird syntax with the asterisk, and you have a thing that looks like a function, but it returns an object and not a thing that looks like a function. It's just complicated and weird, and it's got yield, which can have strange effects on program flow. And we learned in the 70s in the structured revolution that having complicated control flow is a bad thing, and generators appear to be very, very complicated. But even worse than that, they're completely unnecessary. That in JavaScript you can easily write functions if you understand how to or you can easily write generators if you know how to make a function that returns a function. And that turns out to be a pretty easy thing. So I recommend not using the new generators and instead doing things this way. So the pattern is you have the outer function, which I call a factory, which is going to make a generator. And that factory contains the generator's state variables. Any state that the generator needs will be kept in the factory. And then the factory will return the generator function, and when it's called, it will compute the next value and update the state variables and return the new value. So it's a really simple pattern. Let me show you a demonstration. This is the element factory. So I will pass an array to the element factory, and it will return a function. Each time I call that function, that generator, I will get the next element of the array. And you can see how it works. It's really simple. I think this is much cleaner than trying to do things using yield. So we're doing a lot of asynchronous programming now, which requires the use of callbacks. And when you have a callback or continuation is where you have a function that instead of returning a value will receive an extra parameter, which is the function to call to deliver the value. And so there are two ways you could write that. You could put the callback or the continuation as the first argument, or you could do it as the last argument. And because there are two ways to do it, people will do it both ways, and then they'll argue about which way is right. And then we'll have systems which are incompatible with each other because one wants to be called one way and one called the other way, and it's just a nuisance. And unless there's a way of knowing which way is right, that argument never stops. But it turns out ES6 showed us what the correct answer is, and that is it has to go in the first position because we want to have functions that can take a variable number of arguments. And in order to do that using the new ellipsis notation, the callback has to go first. So if you're working with someone who's putting them in the last position, tell them all of their stuff is wrong, and they have to go and fix it. So let's talk about syntax. Syntax is the least important part of a programming language, but it's the part that we fuss about the most. We get really emotionally connected to our syntax, even when it's bad. So I want to show you an example of an if statement through history. So the first one is from Fortran 4. This was my first programming language. And Fortran was developed before lowercase was invented, so we wrote everything all in uppercase. And so we said if, and then parent a dot equal dot 0, a equal b. So Fortran wasn't the first language to use the equality operator to mean assignment, but it was the most influential. And that was a problem, because equality should mean equality. And it used it for assignment. And I can't blame the guys who did Fortran, because they had to work with an extremely small character set. And they didn't have brackets, they didn't have curly braces, they didn't have backslashes. They had a very, very limited set of operators. And so out of desperation, they used the equal sign. I do blame all of the language designers who came after Fortran, because they had better options available, but they didn't use them. So BCPL was the first good parts language. It was a simplification of an earlier language called CPL. BCPL simplified CPL tremendously and just stripped it down. It was a very influential language. It gave us the idea of virtual machines. So the Pascal P machine, the Java virtual machine, all of that stuff comes out of BCPL. BCPL was also the first curly brace language, so that gave us the idea of using curly braces to designate our blocks, which is a really good idea. It used the equal sign to mean equality, which was exactly right, and it used the algol assignment operator for assignment, which was very good too. So I think BCPL got a lot of things right. Then we come to JavaScript, which unfortunately, JavaScript syntax was based on Java, which was based on C++, which was based on C, which was based on B. B was a language which was based on BCPL, but unfortunately, it threw away a number of things that BCPL got right. In BCPL, the parens around the condition of an if statement were optional, and the curly braces around the consequence were required, which was the right way to do it. Fortran didn't do it that way. Fortran had to have the parens in order to separate the if from the A. And unfortunately, B went back to the Fortran model. And unfortunately, all of the languages since then have copied that. So unfortunately, JavaScript is wrong. The curly braces are now optional, which is a problem because the curly braces should always be included every time. That curly braces make it much easier for someone, including people who are on your team that haven't been hired yet, or future you who might forget why you wrote what you did. It's much more likely that someone is going to correctly maintain that code if we always put the curly braces in. And it was a mistake to have defined syntax which left the curly braces out. But if we decide that we don't really like curly braces, there is a better approach. For example, Algol 68, which unfortunately was not a very good language, but I really liked their if statement. They got rid of the curly braces and the begin-end stuff. Instead, they had phi, which was if spelled backwards, which would delimit the end of an if statement. And I think that was really elegant looking. I like that a lot. But I'm sort of becoming a minimalist, and I think we could do better. So I'm thinking maybe the next language wants to look like this, where we just kind of strip it down, make it as simple as possible. So use the colon as the assignment operator. We shouldn't be doing many assignments anymore anyway, but when we do, I'm thinking colon looks pretty nice for that. And we should take the example of Python, that significant white space I think makes sense because white space tends to be significant to us. And so having our interpretation of the syntax match the compiler's interpretation, I think could ultimately reduce errors. So speaking of errors, so here's the try statement from Java. And I think this try statement and its multitude of catches is a problem. So the basic idea is a good one, where we want to try some code and there's a chance it could fail in an unexpected way, and we don't want to have to pass rarely, if ever used, error conditions in every function and have to explicitly check them. For things that should never go wrong, we'd just like to have a more automated way of dealing with that stuff so that our programs are cleaner, and that's a good thing. But Java didn't really do that. So Java provides many, many branches now through this try thing, through the many sorts of catches. And they needed a finally thing at the end. What finally is an implied function call. The code inside of the finally is a function, and it is called automatically in all of the places where this try can exit, including returns and throws and other places. And so you can get very, very complex control flows as a result of that. And Java had to do that because at the time that Java was designed, the language did not have functions. And so there was no other way of taking a piece of code that was common to all of those places and being able to do that. So their lack of functions caused them to put in finally. And then there are all of these catches. And these were motivated by a failure of Java's type system. That most of these things are not things that should never happen, that they're actually things that are expected to happen, routinely happen. You know, that a syntax error is a normal thing to expect from something that does parsing. Or an end is a normal thing to expect from something that's going to be reading a file or a stream. That's not an exception, that is normal. But the Java type system doesn't allow you to communicate that stuff. And so things which are not really exceptions are coded as exceptions, and we get this complicated control flow mechanism which looks a lot like the Fortran computed goto, which is a block of code in which some other entity determines how we go through that block of code, and that turns out to be a really error-prone thing. That's a bad thing about Java. Whereas you look at the way we would write this in JavaScript, and it's a whole lot simpler. So in JavaScript, we don't care about what gets thrown. We don't look at what we got, or we shouldn't. So we just try something. We try plan A. If that didn't work, then we'll try plan B. In either case, we run into the cleanup code and we're done. So it's much, much simpler. JavaScript allows for a function to return any type of thing. So if there are multiple possible return values that make sense, we can return any of those. The type system is not working against us, so we can write cleaner, better programs. So another example of Java's type system getting in the way is in the index of function. So in index of, we've got a string and a substring. We want to see, is the substring inside of the string, and if so, where does it exist? And if not, report that as well. Probably the right way to have written that would be to have it return null or nan or some indicator that we couldn't find it. But Java's type system didn't allow index of to do that, so it instead returns -1, which is a problem because it's a valid int. So if you just take the result of index of and feed it into some other computation, there's a good chance it's going to go wildly wrong, and the type system is not going to defend you against that. So the type system is not protecting you against errors. The type system is actually causing potential errors. And JavaScript could have done better in this case. JavaScript could have returned undefined if it couldn't find the substring, but it just copied the mistake that Java made. So talking more about mistakes Java made. So suppose we want to add two 32-bit integers. What is the type of the result? Can anybody guess? Anybody? Close. It's int33. Int33 is the correct answer because if you add two things that are 32 bits together, you can get a result that's 33 bits. Java says you only get 32, which means that if you got a 33-bit result, it's going to throw away the most significant bit, which is a really serious error. So let's try another one. Multiply int32 by int32. What is the type of that? Very close. The correct answer is int63. int63, because you have the sign bits. The sign bits don't. But you got much closer than Java did, because Java said it's an int32, which is wildly wrong. So again, there's this idea that it has a type system that's protecting us from errors, but it's not. It's actually leading us into errors. And JavaScript, to its credit, does not have this terrible thing in it, which is great. JavaScript has a different terrible thing in it, which is this one. Who has encountered this in their real life? Yeah, this is awful, isn't it? This is inexcusable. We are in the 21st century, and we cannot add 0.1 and 0.2 to get 0.3. We should have fixed this by now. So I think the next language should be able to do this correctly. You shouldn't have to fudge this. And it's even worse than that the order in which you add things is going to change the sum. Okay, so 0.1 plus 0.2 plus 0.3 is not the same thing as 0.1 plus 0.2 plus 0.3. You know, mathematical reasoning, we're talking about pure functional programming, and, think, what's the point of purity if you can't add two numbers? And it's just, so I think the next language should not do this. Our children's language should do better. So this is my proposal for how we fix this. It's a new number type. I call it DEC64. It's stored in a 64-bit word. It contains a 56-bit coefficient, which is just a big integer which contains all of the digits that we're concerned with. And there's an 8-bit exponent which will scale it. So the value of a number is the coefficient times 10 raised to the exponent. That's everything in terms of the encoding of the numbers. So it's really, really simple, really, really efficient. In a software implementation, which you can find on GitHub, we can add two integers together in 5 instructions, which sounds like 5 more than you would really need, except you get overflow protection and nans in those 5 instructions. In a hardware implementation, integers or any two numbers with the same exponent should be addable in one cycle, which eliminates the performance argument for having ints, so we get rid of ints forever and everything goes faster. This is a number type that is ideal for representing all of the numbers that are important to humanity, which are the numbers that are composed of decimal digits. Binary floating point can't do that, but this can. So I'm proposing that this be the only number type in all future application languages, particularly in the next language. So let's talk some more about numbers. So 0 divided by 0, what should that be? Any guesses? So it depends on who you ask. So most mathematicians will say it's undefined. And they don't mean that in the sense that JavaScript means in its silly undefined value. They mean it doesn't make sense to even think about it. Don't talk about it. Shh. We don't talk about 0 divided by 0. It just doesn't make sense. You don't, shh. It doesn't produce a weird value. It doesn't produce anything. You can't even think about it. But computers will do it anyway. So if we have an instruction which is able to divide 0 by 0, it's going to happen. So we could say, but no one will ever write a program that'll do that, so because it doesn't make sense. So it's okay that the machine catch fire, right? Because it's not going to happen, except we know it's going to happen, right? So that doesn't work. Another possibility is we'll return nan or null or some value which says this didn't work. And that's a reasonable thing to do. Another answer is we return 0. And this is actually a reasonable thing to do too, that particularly in business processing. For example, we might have sold 0 units last month, and our total profit on those units was 0. And the boss wants to know what was the average profit per item. And you can't say, boss, shh. No. No, 0 is obviously the right answer. Could be 1, because n over n is 1. Okay. I once worked on a machine where it was 2. If floating point divides 0 over 0, it produced exactly 2. This was a machine that was designed by Seymour Cray, the greatest computer designer in history. And I can imagine a conversation that happened at Control Data. Someone said, hey, Seymour, there's a problem with the divide circuit. He goes, well, what's the problem? Well, if you divide 0 by 0, you get 2. So aren't you going to fix it? He said, look, divide is the slowest, most expensive circuit on the machine. And if I fix it, I'm going to increase the cost of the machine. I'm going to add 1 cycle to all divisions, which is already the slowest instruction in the instruction set. And which means I'm going to slow down every program that does a divide, even the ones that are written correctly, just so that some idiot can divide 0 by 0. What does he expect to get anyway? I'm not going to do it. So he didn't do it. And as far as I know, I'm the only person who ever did it. So let's try another one. 0 times n, what should that be? Any guesses? I think 0 makes a lot of sense, that for any value of n, it should be 0. Infinity is not a value, it's a metaphor, so it doesn't really apply here. So yeah, no matter what n is, it should be 0. And compiler writers who knew this put an optimization in their compilers that at compile time, if they were doing a multiply, and they could determine that either of the operands was a 0 and that the other had no side effects, then they don't generate a multiply instruction, they just emit a 0, and they don't have to evaluate the other argument. So not only does the compiler go faster, but the code goes faster, everything's great. Unfortunately, when the IEEE floating point standard came out, it said if n is nan, then 0 times nan has to be nan, which meant that all of those optimizations were now errors, and they had to back it out, which means that all of the code got slower for no compensating benefit. So who writes code that multiplies 0 by n? Generally, humans don't, because we look to avoid stuff like that, but code processors, or code generators, macro processors, partial evaluators, they do that stuff all the time. And they could all produce much better code if we could multiply 0 by n and get 0. Also, there are non-conditional idioms that take advantage of that. So modern CPUs, one of the things that makes them go really fast is that they have a lot of instruction pipelining. And the instruction pipelines get very, very long and very, very complicated. And everything works fine until you do a conditional jump. And when you do a conditional jump, they can no longer be filling the pipeline because they don't know what the result of the jump is going to be, and so everything stalls until they can figure it out, and then eventually you resume, but that can slow things down. So another style of writing would be, if I've got a value which could be either 0 or 1, I can multiply it by a and multiply b times 1 minus the number and add them together. Even though that sounds like a lot of work, on modern CPUs that could be much faster than doing it the old way with the conditional jump, but that only works if we can multiply by 0. So because of that, I think all of these forms should produce 0, and in fact DEX64 does that. Let's talk about reserved words. So reserved words were intended to make compilers easier to write back when compilers had to run in extremely small memories. Computers used to have memories that were measured in kilobytes, and you didn't have very many of those in your machine, and so having to deal with words which could be ambiguous or used in different situations was really hard. So to make it easier and to make it more likely that the compilers could fit in memory, we came up with reserved words. That's not true anymore. You have gigabytes of RAM in your pocket. It's just, but we haven't rethought the limitations on our programming languages. Reserved word policies come at a cost, that they're a hazard for programmers because if you try to declare a variable that is actually the name of a language feature, then your program is going to fail to compile. It's a hazard for language maintainers because you can't put a new word into the language without risking breaking a program which might already have used that word. In fact, that's why we use throw instead of raise. The original model for exception handling was we would raise an exception. But we couldn't do that because the word raise had already been used and nobody had used the word throw, so that became the word that we used for exceptions. So I propose a different theory that instead, in any function, a word may be used as a language keyword, like if, or as the name of a variable, but not both. So if you decide that you want to have a variable named if, you could write let if, and that's fine, but it means you can't have an if statement in that same function. This is good for programmers because you will not trip over features that you don't use. And it's good for language designers because they can add new keywords to the language without invalidating existing code. So another thing we argue about is how do we deal with names with spaces or multi-word names in a program? How do you deal with that? And so there are two arguments. One calls for camel case, one calls for underbars, and this goes on forever, and neither side can decide who's right. Well, everyone's pretty clear on the other guys are wrong, but that doesn't end the debate. But in this case, it turns out both sides are wrong because the correct answer is names with spaces. So why don't we have names and spaces in our languages? Well, it's the same thing as before, that when you only had a few K to write a compiler, names with spaces made things complicated. But again, we've got artificial intelligence now. We should be able to figure out how to deal with a space. So here's a really simple algorithm, doesn't even need AI. It's actually a very, very simple problem. Something I'd like to see in the next language would be programming by contract. This was something that was in the IFL language, which I thought was brilliant, but it didn't get picked up in anything else. The idea was that you could design a function which will check preconditions when it's called, and will also check postconditions on its return. So when you enter it, it will check its inputs in the current state of everything that it has access to and make sure that everything is consistent and valid and correct and okay for proceeding with the execution of the function. And a similar thing that at the end of the function, everything is also correct. This was a really brilliant idea, that contracts for some cases can do a much better job than types, because the contract is actually written in program text and is embedded in the program and is executable. You can turn the execution on or off, but when you turn it on, you're running tests, integrity tests, in the code as it's running, which is a brilliant thing, that it can be much more specific than types can be. And it's built into the program, which is something that tests can't. So we should have that. I'm hoping that the next language will incorporate programming by contract. Finally, security is becoming a really, really important thing. And our languages were not designed for security. And it's really significant because all of our machines are networked, everything is spread out all over the place. Every machine is a potential point of failure, and our programming languages are not up to the task of securing this stuff. So security should be the first requirement, not an afterthought in the next language. And the programming model of the next language should be about distributed computation, because that is the future. Every language since Fortran has been obsessed with sequential programming. One thing after another, just do that. But that's not the way the world works anymore. We now have clouds, we now have multi-cores, we've got all these ways of writing programs which are not sequentially doing one thing after another. It's sending stuff out. It's a communication model more than a computation model now, and our programming languages don't understand that. I think the next language should be much better at distributed programming. Maybe it's with actors or some other paradigm, but distribution has to be the next thing. Just another sequential programming language, we don't need that. We have enough of those. So that brings me to the end. I just want to warn you to be careful out there because the web is cluttered and full of errors. Thank you.